Velkommen til Learn.tech, en læringsdugnad om teknologi og samfunn, med Silvija og venner.
Hello and welcome to Learn Masters. Our topic today is quantum computing, and our guest today is Dr. Mark Mattingly Scott. I'm Silvija and I'm going to introduce Mark in just a second. I'm going to say 2 words about the series itself. So, Mark, you are now a professor, but in a conversational set of interviews, lectures, 4 lectures at 30 minutes each, where the first one is going to be about the introduction to the subject of quantum computing. The second one is going to be your favorite examples in the topic of quantum computing. The third one will be the tools of the trade. If somebody is considering getting an early move in applying quantum computing, where would they go to start both learning but also doing? And the 4th lecture will be an attempt to do a workshop on, okay, so let's think, how could I apply this? About 30 minutes each and very informal and chatty. So with that, welcome, Mark.
Thank you, Silvija. Good to be here.
So you and I have chatted about the subject before, and every time I try to understand quantum computing, and I have a background in theoretical computer science and maths, my brain gets fried, and you're the only man who managed to get me at least closer to the subject. So I thought I'd like to share this with the listeners of Learn.
Okay.
So thank you so much.
Well, if it's any consolation, my brains are seemingly in a state of permanent deep frying. I can hear the fat sizzling in the background. So you're not alone.
No, it's a consolation to hear that, Mark. So, Mark, tell us briefly about yourself. Who are you, and why do you care about quantum computing?
So, I'm a British guy. The name is Scottish. Well, there's some Scot in there, but I was born in England, so I better say I'm British, otherwise somebody will get offended. I live in Germany, in Heidelberg, and I've been living here for 32 years. I moved over in 1989 from a job in electronics research in London. I'd done my PhD in Durham, in Northeast England. I'd been working in electronics research in London, and I basically got an offer, got asked to come over to Germany to work for IBM as and I call it a midwife to the World Wide Web. So the World Wide Web had just been thought of, so highly scalable hypertext systems, and IBM was interested in this and how to make this work with their products and their platforms, and recruited me and a bunch of other people, and we were the midwives to the web at IBM. 32 years at IBM, or just short of 32 years at IBM. Basically always working on innovative technologies, developing innovative technologies. I left IBM on the 30th of August.
This year?
So, yes, exactly. As this recording happens 13 days ago or 14 days ago. And I'm now what in German is called Geschäftsführer, so managing director of a company called Quantum Brilliance, their German subsidiary, and a general manager of the Australian mother organization for Europe, Middle East, and Africa.
And Quantum Brilliance sounds like is focusing on quantum computing.
It is, and there's a giveaway in the name. So we're, I think we're the only, more or less the only company using or implementing qubits, things called qubits, which work at room temperature, using diamonds, hence the word brilliance. So everybody loves diamonds. We're using them to make quantum computers.
So at least we've started with images that people can start having in their minds, probably completely wrong images. So you'll have to tell us about the size of these diamonds and the role of these diamonds. But before that, can you just open the word qubit for us? What is a qubit?
Yes, I can, or I can try. And I'll try not to fry my own brain. So quantum computing is something truly new, and this is from the mouth of somebody who's been saying this is truly new for to lots of things over the last 30 years. But this time, that statement is grounded in fundamental physics. So we're now able to use a principle of fundamental physics, which was basically exposed about 110, 120 years ago. So up to that point, physics everything had been ticking along nicely, and everything was consistent. And then things happened which led to some contradictions, and was, among others, it was Albert Einstein who came up with an explanation for why this was what might be happening, which then led to the development of a field of physics called quantum mechanics or quantum physics. Out of that, actually starting from the early 1960s, from the year of my birth, 1961, through to the early 1980s, a series of developments where the possibility of using small quantum mechanical systems to perform computations became a dream, and then a possibility, and then reality.
So what you're saying, Mark, is that we are approaching a position where quantum computing might become a practical reality.
I think we're actually there. So it's we have these things called qubits, and a qubit is basically, it's the simplest quantum mechanical system you can imagine. There are a number of ways to actually do that in the practice. What it comes down to is you're either using the so-called magnetic or electromagnetic spin of an electron. Electrons, when they circulate around the nucleus, they either rotate in one direction or in the other direction. You can trick those electrons into having spin, which is, as long as you don't look at them, in both directions at the same time. This is where your brain starts to fry. Or you can use the nucleus, what's called nuclear spin. Or you can use both.
But you basically make these things spin, or you exploit this uncertainty or
Exactly. So the best analogy I have is if you want the answer to a problem, and you can formulate that problem as one of a number of possible outcomes, then
so the cat is alive or the cat is dead.
Yeah, but imagine something much more complex with not just two alternatives, but 2 to the n, thousands or millions of alternatives. Then if you take a truly random number generator and repeat whatever it is you're trying to do enough times, sooner or later it will come up with the right answer. What a quantum computer does is it accelerates that. So it removes the sooner or later and makes that sooner. So what it does is it says for a small fixed number of repetitions of what we call a quantum computing program or a quantum computing experiment, for a small number of repetitions, it will produce a statistically significant answer. So it kind of gets around or cheats pure chance, uses quantum mechanics to speed things. Yes, I can see that's what.
So, to a person who's studying algorithms and complexity theory is my kind of thing, where I was trying to solve this q to the power of n problem by thinking about very smart algorithms. You're actually making me completely irrelevant, because you're saying, don't worry about that. We'll just have a computer that can calculate all those possibilities at once. And we don't have to worry about computational time anymore.
Yes. So you remember non-deterministic Turing machines from your computational theoretical computer
I do.
science?
Maybe you can teach our audience a little bit of the basics of computer science as well.
Well, here's you correct me if I mess this up. So basically, a guy called Alan Turing, who was a genius, worked for the British coding or the Department of Funny Works in the war, decoding or helping to decode the German cipher. Came up with this idea. It's a very theoretical idea of what's called a Turing machine, which is a kind of abstract finite state machine. And he determined that there were computations you can compute on this abstract Turing machine. Essentially, what it looks like.
It's an abstract model of a computer.
Yes and no. He was actually linking it to a physical piece of hardware. So the idea was you have a tape with symbols on the tape. You have a read head which looks at the symbol, and then based on what it sees, it can move the tape forward or backwards, and it can rewrite the symbol. And he proved that there's a very large class of problems which you can solve with this Turing machine. These are Turing computable problems. And he proved that the class of problems that could be solved in what's called polynomial time. So a time proportional to the size of the problem. The whole field of computational complexity theory really took off at the same time as the birth of qubits, so the early 60s, when it became clear that there were other kinds of problems which you could use a Turing machine for to help you with. In particular, class of problems where you could use what's called a non-deterministic Turing machine. And that's one where you basically randomize it and repeat and rinse many times. But at each decision point, you add a random factor. It doesn't really get you anything because you have to repeat. You have to repeat that particular program a number of times, which is combinatorial, basically, proportional to 2 to the power size of the problem. Then quantum qubits came along, quantum computers came along, and we can basically remove that particular constraint. We can find a solution to problems in a similar way to a non-deterministic Turing machine, but much faster. And how does that work?
This is terribly sad for me. No, wait. We're not there yet. But so you can now solve many of the problems that we thought were either unsolvable in any kind of human time, which is the basis of things like, let's say, cryptography, where, you create these security solutions that require computers to compute so much that you couldn't, you have to know the mechanisms, otherwise you can't. And now you can break that with the quantum computing. So there are so many problems, also things that the artificial intelligence does, or, things like materials technology, protein folding, health stuff, other stuff that we will talk about later, which suddenly moves from not just the realm of science fiction, but basically the realm of magic into practicality. I mean,
yeah, there is, it's very strange why that particular, randomness, finding patterns within true randomness, and that quantum mechanics and qubits give you that. Do I have an explanation as to why? Does anybody have an explanation as to why? There are many interpretations about why. So the many universes argument, quantum determinism. I think if you take 11 physicists, then you'll get 12 explanations. Probably the most promising for your listeners is something called quantum Darwinism, which is probably the only explanation which leads to experiments that can actually be performed, and you can look at results and check whether it's false or not. But in essence, the jury is out on why quantum mechanical systems and quantum computers and qubits actually fundamentally why they provide this speed up, but they do. And you're right, there's a large group of problems which, under certain constraints, which we can talk about later, provably accelerate the solution to large groups of problems. And provably accelerate means either exponentially accelerate. That's where it gets really interesting, where, fundamental principles of how society and commerce work change. And then there's another group of problems where you get at least quadratic speed up, and that alone is huge. And we can talk about that. But essentially, go on.
No, I just think that this is where I think I would say that 99.99% of the population, or probably a much larger percentage actually of 100, hasn't come to the point where they've started considering this, because they have more than enough just grappling with AI. And this will move that needle to a completely new level. So I'm again trying to just simplify it. And I want to go back to Moore's law and chips. Mm-hmm. And I'm trying to find a way to understand this a little bit more tangibly. It's really difficult to think about this whole Schrödinger cat problem, and is it alive? Is it dead? We don't know until we open the box, etc. If we think about chips, computer chips, and Gordon Moore, and say 1970, and he notices that these 4 generations of chips seem to be doubling in their efficiency per square centimeter or dollar used to make them every 1.5 years. And then he prescribes this for another 10 years. People laugh at him. He still sticks to his plan. He creates Intel, I think. And
I think it was initially he was from Fairchild, but yeah.
Fairchild, Intel. And later, Fairchild. And then people have been kind of expecting this Moore's law to eventually dry out, and they keep saying, well, you can't do much more. So what I want you to help me understand is the evolution of these chips. So I'm thinking, we start with the big mainframes, and then some years later we figured out how to make these new kinds of chips that were very well suited to desktop computers. And then a whole new revolution follows on back of that. Then we figure out how to make these new chips that are suitable for mobile phones, and a whole new revolution follows on the back of that. Then we figure out how to use these Nvidia chips that are very good for graphics, very parallel, also good for AI. A new revolution follows on top of that. And now with this, you seem to be, moving the limits again. So this is a new revolution based on these qubits that you're creating.
Well, it's not just moving the limits. It's fundamentally changing what the word limit means. So just to draw back the analogy with Gordon Moore, under the assumption that you're building 2-dimensional structures, so on the surface of silicon, then Gordon Moore noticed that the size of what's called the die is the actual, you have a wafer of silicon and you make multiple dies. He realized that the size of the wafers and the size of the dies was increasing constantly. The other factor is what's called the feature size, so the working part of a transistor, which is dependent on processes, which is dependent on things like lithography, precision manufacturing, mechanical precision. He noticed that those feature size were also getting smaller linearly. If you combine those two effects, that leads to a doubling in the number of transistors per unit area. That's Moore's law. When you project that forward from the 1960s, late 1960s, up to today, what has happened in the interim is that you very rapidly reach a point where the communication overhead between different parts of a chip dominates the performance. That's led to particular architectures, computer architectures. So you mentioned, for example, the Nvidia chips, so GPUs, graphic processing units. These are basically large pipelined matrix linear algebra machines. They're very efficient at performing linear algebra on matrices. The whole architecture is optimized for that. They're not much good at doing other things. we now have neuromorphic chips where you simulate neurons on chips. There are other things you can optimize for in the physical architecture on a chip. This is all still two-dimensional. There was some work done on making it three-dimensional, and there's potential there for some building layers. And the very latest processor chips and memory chips are kind of 2.5 dimensional. Okay, now taking all that, you get these scaling factors. The fundamental limit, though, remains an atom. You can't make a chip where the gate is smaller than an atom. Actually, you can't make a chip where the gate is smaller than at least a handful of atoms. Because then, what are you actually switching? Yeah, it's just, what are you switching? Yeah. And with the current state of the art in processor architectures at the feature sizes we're talking about, few nanometers, those transistors are statistical anyway. They are, they have errors. They aren't precise. And you have to compensate for that in the architecture as well. So there's lots of error correcting, ECC, memories, all this sort of stuff. Along comes quantum computing. And quantum computing says, with a single qubit, I can represent not just one of two states, but I can represent all possible combinations of 1 and 2 states, as long as I don't look at it. With 2 qubits, I can represent 4 states, and with 3 qubits, 8. So the number of potential states you can represent at the same time is exponential. That means when you get to a couple of hundred qubits, you've got more potential states than there are atoms in the entire Earth. It very rapidly gets to unimaginable numbers.
So sorry, we need to backtrack. So this is a picture we can have in our mind, but just help me understand, how big is a qubit, and potentially, can I have a computer with a couple hundred qubits, or is it more expensive than all the resources on this planet, or how does it build?
Well, can you have one right now? Difficult. Will you be able to get one in a few years? Certainly. The way you make those qubits is you have to create a quantum mechanically quiet environment, whatever that means. And I mentioned before, there are 2 types. There's 2 ways to implement qubits. One is with electron spin. And with electron spin, you need to create an environment with very low electromagnetic influence, which means it has to be cold, so no thermal energy. So you're at, millikelvin or a few millikelvin. You have to have a very high vacuum, so no molecules bouncing around, hitting your qubits, upsetting their value. And you have to have no magnetic fields, so you need to put it in a special kind of metal container. So those are electronic qubits. You can also use photons to make qubits, photonic systems. They have their own set of challenges because it's difficult to get photons to interact with each other. And one of the things you want qubits to do is to interact with each other and not with the environment. And then there's a third way. There are a couple of other ways, but the third interesting way is to actually not use electromagnetic quantum mechanics, but to use nuclear quantum mechanics, because then you don't really care about the environment. So you can run them at room temperature. You can put them in a diamond, for example. So in 5 years, will you be able to buy a quantum computer? Will there be a GPU card for your gaming PC with a quantum accelerator on it? Probably. That's certainly something my company is aiming for in 5 years. What will it cost? No idea. Will it be affordable? Will it be usable? Almost certainly. So I see a future in 5 years, these things will be in PCs, or potentially in PCs. In 10, 15 years, who knows? I mean, it could be very small.
So we talked a little bit about the origins of this, and we'll have to go back to that again. But I just want to go back to the word revolutionary, because I want to, people are now listening and they didn't know they cared about quantum computing at all. And I'd like them to care. And I need you to help me formulate that once more. So you said revolutionary is almost too weak a phrase. Why?
Because I think in comparison to the technological revolutions which have happened since the 60s, which have all been kind of directly or indirectly driven by the exponential rise in the power of computation. So the internet, World Wide Web, e-commerce, this all the motor driving that has been Moore's law and the power of computation. If I take what Moore's law gives us and I give it a rocket booster, in the sense of, it's a car driving around a Formula One racing track, and suddenly I put wings on it and say, "Oh, you can fly." That's the kind of revolution it is. It opens up completely new areas of exploitation. So, in terms of what, and I don't want to leap forward too much, in terms of what could you do? What might you be able to do? Solving problems which are completely unthinkable today. They're so science fiction we can't even imagine them. You would go, what? Impossible. There are problems out there where we're pretty sure that a quantum computer will be able to answer those kind of questions in a way that will fundamentally change our economies, the way business works, the way we live. So saying it's a revolution is not really enough. It's fundamentally disruptive.
So, two things I want to try to underline here. One is that in a world that's running already on computing power, where everything is controlled by data and computing, getting this evolutionary leapfrog computing animal will be a game changer for those who know how to use it. And then the question is, will we be good at asking the right questions, giving it the right tasks? So we'll get back to examples of where this can be useful in the next lecture. But in the meantime, Mark, can you tell us a little bit about, so we talked about the origins, and we talked about how this thing came about from the quantum physics. I'm still shaky on where did we start making it practical? And then if you could relate it a little bit to the cloud and security problems.
Sure. So I mentioned the early 60s and the 70s as a formative phase for quantum computation. So back in the 60s, a guy called Landauer proved that if you compute things, if you do a calculation on bits, it actually increases the entropy of the universe by a really, really, really small amount, but it does happen. And that was there was a warning signal. Something interesting here. Is there a kind of computation which wouldn't increase the entropy of the universe? And then the early 70s, a guy called Charlie Bennett proved that you could take one of your Turing programs, any Turing program, Turing function, and rewrite it so it's reversible. In other words, you run the program and then you run it backwards, and all you're left with is the original tape and an answer. If you combine those two things, you've got a model of computation that could be run on a quantum mechanical system, because what it says is you do some stuff and then you do it, reverse it, and then you look. And all you see is the answer, and otherwise the universe doesn't care. You've not created or destroyed any entropy. Everything's as it was. You've just got the answer to a question. Then in 1983, I can't remember the exact date, there was a conference on the physics of computation. And among others, Richard Feynman, who the physicists will know his name immediately, the father of quantum electrodynamics, more or less, he said, we could actually use this to compute problems in physics which are hard. Hard means forget it. We can't do it. We can't do anything useful. And in particular, the problem he identified, which would be efficiently computable using such qubits, such quantum mechanical computers, was simulating what's called entanglement, which is where two quantum mechanical systems become entangled, or verschränkt in German. And he showed that is a problem which is horrendous to compute on a classical computer, still is, but is actually quite easy to compute on a quantum computer. And with that, he kind of, the gate was up and the horses are running to see, oh, wait a minute, what else could we do? And then we get into the area of cryptography, and that the leap that happened there, or the significant event that happened there, was again in the early 90s. I think Peter Shaw, who was a professor at MIT, showed a way of mapping a classical algebra problem into a quantum mechanical formulation where it could be solved exponentially faster. And exponentially faster means the difference between billions or tens of billions of CPU years on the fastest computer we have today to a few minutes or hours on a quantum computer with a couple of thousand of qubits. That's a huge difference. And Shaw's algorithm, as it's called, is one of the reasons that the National Institute of Science and Technology is reformulating all the key distribution protocols. They're almost finished with that. And it's why a lot of people want to talk about the impact of quantum computing on security. It's Shaw's algorithm. And in
many ways, we'll get back to the topic of security in our next lecture. But in a way, if I'm trying to simplify again, what you're saying is, and we haven't ever mentioned Claude Shannon or information theory in this series. So then maybe we have to set up a next one with that and Gödel. But
don't get me started on Claude Shannon.
Yeah. No, I'd like to get you started on Claude Shannon, but let's save that. So what you're saying is that until now we've been twisting our brains to formulate problems, find important problems for us humans, and then formulate them in a way that makes them practically computable.
Exactly.
And now
Perfectly,
we can redefine the way that we view, our computing powers in actually just throwing all these real problems at the computer and being able to actually come up with solutions.
So there's a theory called co-evolution, which you encounter in cultural anthropology. If you look at technology and media anthropology, and this is the idea that it was Hans von Forster who formulated it. May be wrong there. It's the idea that humans and human societies develop and evolve and change, and hand in hand with those changes are, of course, humans' imperative to develop tools and improve tools and then use tools for new things. We're very good at that. And with every technological innovation comes a change in organizational innovation. And you've seen this over human history. It's a very robust principle. With classical computation, we've seen this. And you're right. The problems we think of as, well, the ultimate thing we can solve with a computer are, in effect, if you look at it the other way around, they're just the things that we can solve using today's computers. That moves on, it gets faster and faster and more of it. But essentially, it's very difficult to think about what would happen if I had this limitation, if I completely threw it out the window. Quantum computing is throwing the limitations, not all of them, but a lot of them, throwing those limitations out of the window. So in terms of what can we do with it, it's a fundamental change in a way that the invention of the silicon chip and the transistor wasn't. It goes much further.
So, final question here, Mark, before we end this first lecture. I was reading some bits from Guns, Germs and Steel the other day.
Ah.
And one of my kids asks me, so mommy, if the Chinese invented gunpowder, how come they didn't invent guns? Or how come they were not invented there? And this cultural side of innovation is an amazingly fascinating thing related to what you talked about here. You know, we invent technologies that fit with our culture. And without going too far into this determinism discussion, you know, quantum computing as this immensely powerful game changer and human nature, you know, what are your thoughts on that? Should it be somehow very carefully handled as a, you know, very dangerous medicine, or?
Well, you're touching on all sorts of sleeping dogs and skeletons there, potential skeletons. So it's not even potentially, it is a strategic technology, that's for sure. If you look at where did quantum physics happen, where did most of the physicists live and work, a significant proportion of them came from the German-speaking world, Germany, Austria, Switzerland. Those three countries are dotted with people who formulated quantum physics. So there is a heritage in Central Europe. And there is still, if you look at the university, the academic environment around quantum physics, quantum mechanics, quantum computation, quantum chemistry, I mean, Germany is, you know, it's just like, it's incredible, the density of research happening in Germany. Historically, we've always seen that the Anglo-Saxon world, in particular the Anglo-Saxon world to the west of us, across the Atlantic Ocean, is very good at exploiting technologies. They're certainly putting their foot on the gas pedal for quantum technologies. Is there an opportunity for Europe to lead? Yes, definitely. Is it too late? No. But we've got a lot of catching up to do because the US is very much driving forward. And you mentioned gunpowder in China. China is also investing multiple billions in quantum technologies in general and quantum computing specifically. And it will be a society forming technology. I don't think there's any doubt about that. So the short answer is it's a game changer both at the economic, business and societal level. You didn't ask this, but it was implicit. How is Europe positioned? Definitely could do better, but there is a lot of potential to overtake the other two because the game is by no means over yet. And that's one of the reasons my company has moved to Germany, is we want to be, we see Germany as key. But the other European countries, almost all the other European countries, have a definite value to add in that equation. And I
think we have to stop talking about this as blue sky research and
yes.
And move it down to something that's in our hands.
Definitely.
Mark, thank you so much for this first lecture. We'll meet again in a couple of minutes for the next one.
Du har nå lyttet til en podcast fra LØRN.tech, en læringsdugnad om teknologi og samfunn. Nå kan du også få et læringssertifikat for å lytte til denne podcasten på vårt online-universitet LØRN.nbsp.